Okay, we are in 3.5, which is infinite limits. And we have talked about infinite limits, I think, before, but I wanted to define them a little bit more carefully this time. And so I want to look at f of x equals 4 over x minus 3, and specifically I want to look at the limit as x approaches 3. Now why do I want to look at that? Well, of course, because that is where the denominator will be 0. In fact, if I try to plug this in, right, when I'm applying my limit ideas, what I told you was to plug in the value, and I get 4 over 0. And this immediately tells me that my limit is going to be infinite. Okay, and so I know that that means it does not exist. Right, there's my does not exist. And when it doesn't, right, we like to explain why it doesn't. Okay, because the reason that we're looking at it in the first place was probably because we knew that something interesting was going to happen there. And so we want to look at the right and the left-hand limits separately. So we're going to look at the right and the left-hand limits. We're going to let our knowledge of graphs help us here. And so I have the graph here. Okay. So I have this already defined here. Oops. At f of x equals x minus 4 over x minus 3. Okay, so this is my graph. It's actually, if you recall the way that we shifted graphs and things like before, this is the graph of 1 over x. It's shifted right 3 units, okay? And so I get the vertical asymptote at x equals 3. And so I want to write this behavior, okay? So if I look at the first one I have here is, it has with the 3 with the plus, so that means from the right of 3, from bigger numbers than 3. Okay, so if I come over here and I look at my graph, oh, my phone is okay. So my graph over here, I'm coming, and as I approach 3, it's going straight up. Means that my y value is increasing without bounds, and so we say that this is infinity, and this means in English increases without bounds. Increasing without bounds. All right, if we look at the other side, as we approach 3 from the left, on this side to the left of 3, I'm coming and my graph just falls right down. And so my y values are just plummeting. So I'm going to say, in this case, we say that that is negative infinity. I know that doesn't exist, but we still write this to describe the behavior of the graph there. So this is decreasing without bounds. So they're doing opposite things, so I need to leave them separate. If I came across an example where I looked at as x approaches 3 from the right was infinity and the left was infinity, then I could write it overall as the limit as x approaches 3 without the plus and minus is equal to infinity as well. But as long as they're different, I need to keep them separate. Now, if I didn't know what the graph looked like, okay, so now I have the table set up in here. And so the original way that we learned how to look at limits, now we don't do that anymore because it's only an approximation, okay, but we could just use a table. And so if I plug in, so I've got my table here, from the right I plug in 3.1 and I get 40, 3.01 and I get 400, 3.001 and I get 4,000. So every time I increase my x value just the smallest little tiny bit, then my y values are making big jumps and they're positive, so that's another way to show that it's going to positive infinity. And as I approach 3 from the left, this time starting from the bottom and working my way up, I go from negative 40 to negative 400 to negative 4,000. So even though my x value is barely increasing, my y values are making these giant jumps, right, by another power of 10 essentially. Okay, so that's a good way because my values keep getting more and more negative to justify the fact that it's going to negative infinity. Okay, so this is the one time when you can use a table to justify, but that's only for infinity and negative infinity. Right? Otherwise, we can't make tables anymore for the other ones. We have to use what we know about algebra. Okay, so one more thing that I wanted to talk about in this particular section is infinite limit properties. Okay, and so we have some here. So this is, now we've learned that we can add, subtract, and multiply these if the limit exists, but I also want to talk about what happens if one of these limits is infinity, okay? So if I have the limit of f as x approaches c just being a constant, and it's infinity, right? It's an infinite limit, and g, the limit exists, and it's a specific number, so L is a constant. It kind of looks like Lisa constant, but it means L is a constant here. That's what I meant by this little blurb over here. So this limit exists and it's a specific number. This limit is infinity. It really kind of fails to exist, okay? So just some properties when we use infinity. So if I add f plus g together, and the limit as f is infinity and the limit of g is L, then infinity is like this huge number, right? It's I can't put my finger on it, it's so big. But if I add it to L, then that just makes my infinity even bigger. So a constant just gets swallowed essentially by infinity. It just makes infinity even bigger, okay? And so we say that if I have a number plus infinity, then I'm going to get infinity back. All right, so if I multiply f and g, then I get also infinity, because infinity times a number is infinity, assuming that all the rules of positive and negative multiplication and numbers apply. So if my limit is positive and I'm approaching it and f is infinity, then a positive times infinity gives me positive infinity. If my limit happened to be negative, which it can be, then f times g would be infinity times a negative number, which would give me negative infinity. So it's just the rules of multiplying negative numbers together that give us that. Okay, so now I think that those kind of make sense, right? If I add a infinity and I add a little bit or subtract a little bit from it, then I still get infinity. It's really this giant thing that I'm not really changing very much. And if I multiply two things, a constant times infinity, then again, I still get a really giant thing, whether positive or negative, just based upon my sign of L. Then the last thing, so if I divide f divided by g, remember f is the thing that had the limit was infinity and g was a constant. So if I take infinity and I divide it by a constant, that's still infinity. It's a little bit smaller, but it's still a giant number, because we think of infinity as this really, really large thing. But the really interesting thing, though, is when I reverse this. So this means my g, the limit, let me just write this out again here because it's up a little far. The limit as x approaches c of g was a constant, right? It was L. And then the limit as x approaches c of f, this was the infinity. So really I have a constant divided by infinity. And whenever we're taking the limit of something that turns out to be like this, then essentially we call this zero, because as it gets big, the denominator keeps getting bigger and bigger and bigger and bigger, and I'm just taking this measly little constant and dividing it by a bigger and bigger value, then we essentially say it shrinks and it becomes zero. Okay.